Okay, the rest of the sections in chapter 6, they each can kind of be treated individually. This is what we did in class that I'm afraid was a bit confusing because I did 6.1 and then 6.2, and now I realize it was probably I should have done it in reverse order. 6.1 is the extreme value theorem. That's what this is about. Extreme value theorem. And we will use this when we have a closed interval of a continuous function. And this is based on the fact that if you have some continuous function and you have some closed interval, let's say from A to B, we close it off between A and B, you are guaranteed to find the highest point or the lowest point somewhere on that interval. So it could be that the lowest point, if I look at this, this looks like the lowest point and this looks at like the highest point. Here's the thing, the lowest point will either occur at a critical value where the slope is 0 or undefined. Here's the critical values and here's the endpoints of this graph. Or it will occur, I don't know why I called that B, sorry. Or it will occur at an endpoint, either at the endpoint A, the endpoint B, or at some critical value in between. So this is where, excuse me, we don't have to go up and test it like we did in section 5.1, 5.2, 5.3, 5.4. This is where we just plug everybody in. What are the possibilities? Well, the possibilities are that the highest or the lowest value will occur at the endpoints or at the critical values. So we plug all these in, and the highest value is the absolute maximum on that interval, and the lowest value is the absolute min on that interval. Now what is the same as 5.1 and 5.2 is how we go about figuring out what the critical values are. We take the derivative, we set it equal to 0, solve for x, and that's how we come up with what the critical values might be in the first place. The examples that we're going to use for this, and I did make a video on this that you're going to receive, are on page 345, 21, 50, 58, and 61. All right, now the next section is 6.3. This also is completely sort of contained by itself. You don't have to really think of it as related to anything else. This is economic lot size. They all contain a derivative of somehow, but this is not, you can kind of just contain this in its own, seal it off in its own little bucket, sort of. So this is about economic lot size. I keep wanting to write an E. Economic lot size. And I don't know why that C is so big. Okay. And the economic quantity size. So we'll be calculating how to find the most economical lot size to manufacture, or the most economical quantity size to order, if you, as far as space goes and things like that. So it's just mostly a formula that we use. It's not that hard. In addition to that, we're going to be looking at elasticity of demand. And so this is sort of a measure of how a change in price affects demand. So these are the topics in section 6.3, but again, it's almost like we could close it off in its own little box and do it without worrying about the other sections. It was developed, the formula we will use was developed using a derivative, but I think that's about the only relation that, and they just tied it in here, which is fine, but I don't want you to be confused. So we're going to look at that. I will make a video. I haven't made it yet, but I plan on making a video to send you on this because I don't know if we'll have time in class. And the examples I plan on doing are page 365, numbers 14 and 15, and then on page 362, example 3, on page 364, example 5, and then page 366, number 27 and 28. Now, you know I like worksheets, so all these examples I'm writing down, I'm telling you, but I'm also planning on sending you a worksheet with those specific examples right there for you to see. All right, so I owe you this one. I made the other 3 today, and so you'll be getting those. All right, the last thing that's on the test is section 6.4, and again, it could almost be in its own little section. It is a new way. It's called implicit differentiation. So it is another way to find a derivative. Now, why do we need another way to find a derivative? Well, we use this method when you have an equation that has x's and y's on both sides of it, and it's not easy to solve for y. So if you have something like x squared plus y squared is equal to 2y, it is not really easy to solve for y and get it by itself on one side of the equation, like we have seen in every single example we've done so far. So we're going to learn a method called implicit differentiation to help us find the derivative y prime when we have a situation like that. So what will we do with this once we find the derivative? Well, we'll do every single thing that we know how to do with the derivative, which is figure out when a function's increasing or decreasing, figure out the slope of the tangent line, figure out the equation of a tangent line, whatever we have done so far to figure out this rate of change of the function. This is just a new method we're learning to be able to do that. And we will do this in class on Thursday. So I don't plan on making a video, but I probably will have a worksheet for you because you know how I am. I will see you guys soon.